most of our times.
You may have heard that computers work on ones and zeros. Or you may have seen scary-looking visuals like this. But almost nobody today actually deals directly with these ones and zeros. But ones and zeros do play a big role in how computers work on the inside.
Inside a computer are electric wires and circuits that carry all the information in a computer. How do you store or represent information using electricity?
Well, if you have a single wire with electricity flowing through it, the signal can either be on or off. That's not a lot of choices, but it's a really important start. With one wire, we can represent a yes or a no, true or false, a 1 or a 0, or anything else with only two options. This on-off state of a single wire is called a bit, and it's the smallest piece of information a computer can store. If you use more wires, you get more bits. More ones and zeros, with more bits, you can represent more complex information. But to understand that, we need to learn about something called the binary number system.
In the decimal number system, we have 10 digits from 0 to 9, and that's how we've all learned to count. In the binary number system, we only have 2 digits, 0 and 1. With these 2 digits, we can count up to any number. Here's how this works. In the decimal number system we're all used to, each position in a number has a different value. There's the 1 position, the 10 position, the 100 position, and so on. For example, a 9 in the 100 position is a 900. In binary, each position also carries a value, but instead of multiplying by 10 each time, we multiply by 2. So there's the 1's position, the 2's position, the 4's position, the 8's position, and so on. For example, the number 9 in binary is 1001. To calculate the value, we add 1 times 8 plus 0 times 4 plus 0 times 2 plus 1 times 1. Almost nobody does this math because computers do it for us. What's important is that any number can be represented with only ones and zeros, or by a bunch of wires that are on or off. The more wires you use, the larger the numbers you can store.
With 8 wires, you can store numbers between 0 and 255. That's 8 ones. With just 32 wires, you can store all the way from 0 to over 4 billion. Using the binary number system, you can represent any number you like. But what about other types of information, like text, images, or sound? It turns out that all these things can also be represented with numbers. Think of all the letters in the alphabet. You could assign a number to each letter. A could be 1, B could be 2, and so on. You can then represent any word or paragraph as a sequence of numbers. And as we saw, these numbers can be stored as on or off electrical signals. Every word you see on every web page or your phone is represented using a system like this. Now, let's consider photos, videos, and all the graphics you see on a screen. All of these images are made out of teeny dots called pixels, and each pixel has a color. Each of the colors can be represented with numbers. When you consider that a typical image has millions of these pixels, and a typical video shows 30 images per second, now we're talking about a lot of data here.
Every sound is basically a series of vibrations in the air. Vibrations can be represented graphically as a waveform. Any point on this waveform can be represented by a number. And this way, any sound can be broken down into a series of numbers. If you want higher quality sound, you would pick 32-bit audio over 8-bit audio. More bits means a higher range of numbers.
When you use a computer to write code or make your own app, you're not dealing directly with these ones and zeros. But you will be dealing with images or sound or video. So if you want to understand how computers work on the inside, it all comes down to these simple ones and zeros and the electrical signals in the circuits behind them. They are the backbone of how all computers input, store, process, and output information.
Hi guys, this is Mr. Mojer. So we started to learn a little bit about binary. That's a type of number system basically. Let me switch my marker here. I don't like... Yeah, let me get wire. Yeah, that's still too thick though. I want it to be smaller. There we go. Okay, so we have started to discuss binary, and now we're going to do some really fun activities with it. Let me grab a different color here. So you guys are already familiar with the number system that we use all the time. So for example, if we have the number 572. Well, if we think about, let me change the color here actually. So if we have 572, we know that the 2 represents just, well, 2. But what does the 7 represent? It's actually worth 70, right? And the 5 in 572, well, that actually represents 500. And that's a system that we're used to. So if we did another example, let's say we did, and let me get some fresh screen here. Let's say we did 368. Well, in that case, the 8 would just represent, well, 8. The 6 actually represents 60. And the 3 actually represents 300. So this is what we're used to. But in binary, it doesn't go from the ones place to the tens place to the hundreds place. Binary has its own rules. So in binary, each place doubles. So the first place is the ones place, and then times 2 is the twos place, and then 2 times 2 is 4, so we have the fours place, and the eights place, and so on and so forth. So let's say that we had, and the only thing that can go in each of these places is a 1 or a 0. So let's say that, for example, we had 0 8s, 0 4s, 0 2s, and 1 1. Well, that would be equal to 1. What if we had 0 0 1 0? Well, this we'd have 0 1s, we'd have 1 2, we'd have 0 4s, we'd have 0 8s. So what would that equal? Well, that would equal 2. Okay, so if we wrote 0, let me do this actually. Remember, our places are 8, 4, 2, and 1. Let me switch colors here. Hope that's not what I wanted. So if we had 0, 0, 0, 1, we just have a 1 in the ones place, so that's equal to 1. Then how could we write 2? Well, we could say 0, 0, 1, 0, and all we have is a 2, so that would equal 2. Now, kind of the challenge question is, well, what does 3 equal? How could we write 3? So I'm going to give you a second to try to figure that out. How would you write 3? Okay, this is what I would do. 0 and 0. Then we'll need 2 and 1 together. So we need a 2 and a 1. 2 plus 1 equals 3. All right, now how would we write 4? Well, to get to 4, oh look, there is an actual 4's place. So we would say 0 8s, 1 4, 0 2s, 0 1s. That would equal 4. The next one's going to be a little tricky. How would we write 5? Well, we would need a 4 and a 1. So we would say 0, 1, 0 2s, and we need 1, 1. So we have a 4 and a 1, a 4 and a 1 together are 5. So I hope you're starting to get the idea. Now, the reason that this counting system is so useful is because computers use electricity that can be on or off. So all you have to think of is like a 0 is like off and a 1 is like on. And you can start to think how a computer is able to store information using just electricity. That's how we can save things. Like if you save a document, click save, it's actually using electricity on or off to save the thing that you've created. So let's take a look at some kids in a classroom learning about this system.
Hey, so today we're going to learn about binary digits. So hands up if you've heard of a thing called a bit in a computer. Have you heard of a bit? Okay. Do you know what? A bit comes from binary digits. We take the first letter of binary and add the last bit of digit and we shorten it to bits. So right now we've got 5 bits just standing up here. So let's see what that means. I'm going to give you the number 1. You're going to be a bit that represents 1 dot. You're going to be a bit that represents 2 dots. What's the next number? Call it out.
4, 3.
Hands up if you think 3. Okay, that's our counting system. Let's see if you're right with binary. Oh, it's 4. What could be the next number? What could be the next number? Yep.
6 or 5.
It could be 6 or 5. It's actually 8. So what's happening with those numbers? What's the next number, Oliver?
16.
Is he right?
Yep.
What's the next number after 16 then? Jacob?
32.
Ah, what comes after 32?
126.
Could be. What else could it be? Lachlan?
64.
Is he right?
Yep.
Yep. What's the next number that comes after 64? Thomas?
28.
After that? Jacob?
256.
There we go. Does anyone know what the next one is, Ben?
112.
So, what's the next one, Jacob?
1024.
So with only a few bits, we can count up really high, right? So if we look at this, we can count 1, 2, 4, 8, 16 dots. So let's look at what that means inside a computer. A bit can be on or it can be off. So this bit can be on or it can be off. Right, now what I want you guys to do is to think of a number between 31 and 1. Hands up if you thought of a number. Ben, what number?
12.
12, right. What we want to do is look at these dots and show 12 dots in binary. Do we want 16 on and off or off?
Off.
Cool, turn off please. If we're making the number 12, do we want 8 on or off?
On.
Okay, how many's left over then? Okay, so do we want 4 dots on or off?
On.
What about 2?
Off.
Why? Why is 2 getting turned off?
Because you've already made 12 with the 8 and the 4.
Ah, so 1 stays on or?
Off.
Okay, so who can tell me in binary what 12 would be, representing 12? Who wants to have a go? William, go.
Off, on, off, off.
Thumbs up if you agree. Cool. What about Elan? Do you want to make, can you guys turn yourselves all back on again? Elan, choose a number that we're going to make.
24.
24, cool. So, Logan, can you just turn yourself back on, please? So, for 24, do we want 16 on or off?
Yeah. On.
8, on or off?
On.
4,
Off.
2,
Off.
1.
Off.
Huh. So, Elan, what is binary for 24 dots?
On, off, off, off.
Could we make the number 1 for me? So, how would we do that? How would we make the number 1? Go.
Black, 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 and white.
Cool. Can you guys make that? Now that you've seen the number 1, is there another number you can think of that would be even lower than 1? Will?
0
How would you make 0?
turns the 1 off as well.
Okay, turn on. So we can make the lowest number is 0, and the highest number, if you turn all of your cards back on, with 5 bits, what's the highest number we can represent? Ben?
31.
Hands up if you agree with Ben. So many people can't be wrong. It is, it's 31. So if we can make 31, what's the next card going to be? If I join this and it become the 6th bit, what's the next number? 32. If I turn on 32, these guys all have to turn off to make 32, right? So if you guys all turn off? Cool. So let's do some counting and see what happens with the different bits. So we've got 0. What do we need to do to make 1? Yep, give the instructions.
On 1.
Cool. 2? How do we make 2? Tell the people.
Turn off 1 and turn on 2.
3? Lachlan, go.
Turn 1 on and keep 2 on.
4? 4. William?
Turn 2, turn 1 off and turn 4 on.
5? Jake?
Turn 1 on.
Okay. What are you noticing about the first bit?
So we kind of saw how they were doing that activity in class. What they did was they had these different cards that were storing the different amounts. So we have a card for 1, a card for 2, a card for 4, 8, and 16. So if I wanted to have the number 1, I would just have the 1 card on, and I would turn off all the other cards, and now I see 1 dot is visible. Well, if I wanted to have 2, what would I need to do? I would have to turn off 1 and turn on 2. What if I wanted to have 3? I would have to turn 1 on. Now let's show them all again. Now, what if I wanted to make 10? What would I have to do? Well, to make 10, I could use 8 and 2, because 8 and 2 are 10. So I would turn off the others. So I have 8 and 2, which would leave 10 dots visible. Now, what if I wanted to go to 11? I could turn this over. Now I have 8, 9, 10, 11 dots. Now what if I want to go to 12? That gets a little trickier. Let me show all the cards again. How could I make 12? Well, I could have 8, 9, 10, 11, 12. Okay, I need 4 more. So I would need the 8 card and the 4 card. And that shows 12 dots. Now, here is your challenge activity. So on a piece of paper, I've kind of shown you here how you could write 1, 2, 3, 4, 5. I want you to write in binary. Remember, it goes in binary. It goes 1, 2's place, 4's place, the 8's place. And if I wanted to write 5, for example, let me change the color. If I wanted to make 5, I would need 0 8's. I would use 1 4. I would use 0 2's. I would use 1 1 because then I'd have 4 and 1, which equals 5. I want you to see what, and you can do this on your own paper, what would I need to do to make 8? What would I need to do? Let me get a different color here. What would I need to do to make 9? What would I need to do to make 12? What would I need to do to make 19? So try to work those out. And there's also a way that we can go on and represent letters to spell out words too. But I think we'll probably get to that another day. So, if you haven't finished already, you can pause the video. Now let's work through some solutions together. So to make 8, well, there's actually a place for 8. So I would just say, oh, okay, 8, then I don't need anything else. Now, if I wanted to make 9, I would use an 8 and a 1. So I would say 1, 8. I need 0 4's, I need 0 2's. Okay, now let's look at 12. I think 12, okay, 8 and 4, 8, 9, 10, 11, 12. So if I have 1, 8 and 1, 4 together, that's 12. Now let's go to 19. I think this one might be a little tricky. So 8 plus 4 is 12, plus 2, 13, 14, and one more, 15. Oh, shoot. Wait a second. 8 plus 4 is 12, 13, 14, 15. I can only go to 15. What would I have to do? Well, I'd have to go on to the next place. Remember, they're all doubling. 1 times 2 equals, from here we start at 1, then we double it and go to 2. We double it, go to 4. We double it, go to 8. If we doubled 8, what would that be? 16. So then if we're trying to get to 19, we could do 1, 16. So we have 16. We don't need an 8. 16 plus 4 is 20, which is too much. So we don't need that. So we'd have 1, 16, 17, 18. Oh, we would use a 2, which would get us to 18, and 1 more, which would get us to 19. All right, you can go ahead and make other numbers if you'd like. You can actually make any number using binary, just like we can in the regular number system that we use. Well, I hope you enjoyed learning a little bit about binary. This is a really important part of how computers can remember information, and I hope to see you soon.